Alright, I apologize for the background noise, but I'm at Ike's. I'm gonna adjust the gain just a little bit. A lot of background noise. There's a couple things I want to learn and read just to have the knowledge, I don't know, just to get it through my head a little bit. And I guess I'll just start with this short chapter. 7, 8, and 9 really is what I want to go through. And I plan to just straight up skip equations. It doesn't make any sense when I listen to it, so if you're looking at it, you can feel free to pause it, look at the equations. I will just say skipping equation. 7, dimensional analysis, similitude, and modeling. Learning objectives. After completing this chapter, you should be able to apply the Buckingham Pi Theorem, develop a set of dimensionless variables for a given flow situation, discuss the use of dimensionless variables in data analysis, and apply the concepts of modeling and similitude to develop prediction equations. Although many practical engineering problems involving fluid mechanics can be solved by using the equations and analytical procedures described in the preceding chapters, there remain a large number of problems that rely on experimentally obtained data for their solution. In fact, it is probably fair to say that very few problems involving real fluids can be solved by analysis alone. The solution to many problems is achieved through the use of a combination of theoretical and numerical analysis and experimental data. Thus, engineers working on fluid mechanics problems should be familiar with the experimental approach to these problems so that they can interpret and make use of data obtained by others, such as might appear in handbooks, or be able to plan and execute the necessary experiments in their own laboratories. In this chapter, we consider some techniques and ideas that are important in planning and execution of experiments, as well as in understanding and correlating data that may have been obtained by other experimenters. An obvious goal of any experiment is to make the results as widely applicable as possible. To achieve this end, the concept of similitude is often used so that measurements made on one system, for example in the laboratory, can be used to describe the behavior of other similar systems outside of the laboratory. The laboratory systems are usually thought of as models and are used to study the phenomenon of interest under carefully controlled conditions. From these model studies, empirical formulas can be developed, or specific predictions of one or more characteristics of some other similar system can be made. To do this, it is necessary to establish the relationship between the laboratory model and the other system. In the following sections, we will find out how this can be accomplished in a systematic manner. That's not good. Close program. No, that's this program. Shit. 7.1. Alright, we'll close this. And this is processing. I can close this. Open this. This. 7. Whatever, there's only one page in, right? Dimensional analysis. Alright, don't break again. To illustrate a typical fluid mechanics problem in which the experimentation is required, consider the steady flow of an incompressible Newtonian fluid through a long, smooth-walled, horizontal, circular pipe. An important characteristic of this system, which would be of interest to an engineer designing a pipeline, is the pressure drop per unit length that develops along the pipe as a result of friction. Although this would appear to be a relatively simple flow problem, it cannot generally be solved analytically, even with the aid of large computers, without the use of experimental data. The first step in the planning of an experiment to study this problem would be to decide on the factors or variables that will have an effect on the pressure drop per unit length, the delta P sub L skipping equation. We expect the list to include the pipe diameter d, capital D, the fluid density ρ, the fluid viscosity μ, and the mean velocity v, at which the fluid is flowing through the pipe. Thus we can express the relationship as delta P sub L equals F skipping equation, which simply indicates mathematically that we expect the pressure drop per unit length to be some function of factors contained within the parentheses. At this point, the nature of the function is unknown, and the objective of the experiments is to be performed is to determine the nature of this function. To perform the experiments in a meaningful, systematic manner, it would be necessary to change one of the variables, such as the velocity, while holding all others constant, and measure the corresponding pressure drop. This series of tests would yield data that would be represented graphically as illustrated in figure 7.1a. It is to be noted that this plot would only be valid for specific pipe and for the specific fluid use and tests. This certainly does not give us the general formulation we are looking for. We could repeat the process by varying each of the other variables in turn, as is illustrated in 7.1b, c, and d. This approach to determining the functional relationship between the pressure drop and the various factors that influence it, although logical in concept, is fraught with difficulties. Some of the experiments would be hard to carry out. For example, to obtain the data illustrated in figure 7.1c, it would be necessary to vary fluid density while holding viscosity constant. Yeah, right. How could you do this? Finally, once we obtain the various curves shown in figure 7.1, A, B, and C, and D, how could we combine these data to obtain the desired general functional relationship between these variables, which would be valid for any similar pipe system? Fortunately, there is a much simpler approach to this problem that will eliminate such difficulties. In the following sections, we will show that rather than working with the original list of variables as described in 7.1, we can collect these into two non-dimensional combinations of variables called dimensionless products or dimensionless groups, so that, skipping equation, but it's some stuff, and then a phi of some stuff. Dimensional analysis, similitude, and modeling continued. Thus, instead of having to work with 5 variables, we now have only 2. The necessary experiment would simply consist of varying the dimensionless product and determining the corresponding value. The results of the experiment could then be represented by a single universal curve as illustrated in 7.2. This curve would be valid for any combination of smooth-walled pipe and incompressible Newtonian fluid. To obtain this curve, we would choose a pipe of convenient size and a fluid that is easy to work with. Note that we wouldn't have to use different pipe sizes or even different fluids. It is clear that the experiment would be much simpler, easier to do, and less expensive, which would certainly make an... Oh boy. Did I read this before? The basis of this simplification lies in a consideration of the dimensions of the variables involved, as was discussed in Chapter 1. A qualitative description of physical quantities can be given in terms of basic dimensions, m, l, and t. Alternatively, we could use f, l, t as basic dimensions from Newton's second law. F is ml over t squared. Recall from Chapter 1 that weird equal sign with a dot over it is indicating dimensional equality. Not only have we reduced the number of variables from 5 to 2, but also the new groups are dimensionless combinations of variables, which means that the results presented in the form of 7.2 will be independent of the system of units which we choose. This type of analysis is called dimensional analysis. It can be used on a wide variety of problems. And now we take a look at Buckingham Pi Theorem. The fundamental question we must answer is how many dimensionless products are required to replace the original list of variables. The answer to this question is supplied by the basic theorem of dimensional analysis that states the following. If an equation involving k variables is dimensionally homogeneous, it can be reduced to a relationship among k-r independent k-r independent dimensionless products, where r is the minimum number of reference dimensions required to describe the variables. Or, if we read this, if equation involving k variables is dimensionally homogeneous, it can be reduced to a relationship among k minus r independent dimensionless products, where r is minimum number of reference dimensions required to describe the variables. In Mother Russia, Pi Buckingham's U. The dimensionless products are frequently referred to as pi terms, and the theorem is called Buckingham Pi Theorem. Edgar Buckingham used the symbol capital Pi to represent dimensionless product, and this notation is commonly used. Although the Pi theorem is a simple one, its proof is not so simple, and we will not include it here. Many entire books have been devoted to the subject of similitude and dimensional analysis, and a number of these are listed at the end of this chapter. Students interested in pursuing the subject in more depth, including the proof of the Pi theorem, can refer to one of these books. The Pi theorem is based on the idea of dimensional homogeneity, which is introduced in Chapter 1. Essentially, we assume that any physically meaningful equation involving k variables, such as u of some things, the dimensions of the variable on the left side equal the sign on the right. Then follows that we can rearrange the equation into a set of dimensionless products. Okay. Determination of pi terms. Alright, so this is it. Several methods can be used to form the dimensionless products or pi terms that arise in a dimensional analysis. Essentially, we're looking for a method that will allow us to systematically form the pi terms so that we are sure that they are dimensionless and independent and that we have the right number. The method we will describe in detail in this section is called the method of repeating variables. It will be helpful to break the repeating variable method down into a series of distinct steps that can be followed for any given problem. With a little practice, which is what I still need, you will be able to readily complete a dimensional analysis for your problem. Yay, that's great news. Maybe I should start a new video. I kind of want to. Shit. Okay, I'm gonna stop this one. How do I get out of here? Get out. Okay. And hey, thanks for watching this one. I'm gonna make a new one that's just the steps. Alright. Where is it? Okay, outputs.